All right, so where we had kind of gotten to on the last time is we had started to introduce this idea of entropy as kind of one of the bigger ideas that we started to talk about here. And I made you the promise that we will talk more about it later. We mention it here, we talk about it here, we kind of make an argument here from disorder. And then we will come back and actually learn a little bit about how to calculate entropy. And then we will learn about how it's really hard to calculate entropy. But in reality, I mean, right? So remember, kind of one of the things, and I talk about this to my organic students quite a bit too, because it's more prevalent there. One of the things to remember is that what we're talking about here and what we're discussing here is chemistry that is done on paper, right? So there's certain benefits that come with that in terms of simplifying things and all that kind of stuff. But I think as you guys, what are you guys doing in lab this week? Like the enthalpy of ice? Is that what it is? Is that what's going on?
Freezing point.
The freezing, that's what it is. Yeah, okay, yeah. So what you guys will find, in case you haven't already discovered it in the chemistry lab or any of your other labs that you guys have to take, is that science in reality is very different from when science happens on paper, right? So, but and entropy is one of those things that definitely is a lot more difficult to discover in reality than on paper. But that's coming up, right? All right. So today we might get through the rest of chapter 13 today. And then, we'll spend a little bit of time on Friday going through some of like the example problems, or a couple more example problems from the chapter in the book and those kind of things. I should have the quiz at least done for you guys later on today, and then Friday it'll open up and it'll be due at the end of Friday, right? So basically you guys have all day Friday to do it. So set aside, at least 8 hours to get it done.
Only the exams take me 8 hours.
Yeah, don't worry. No, it won't take you guys that much time, but make sure you guys do, set aside some time on Friday to keep an eye on the quiz there on campus and get it done, okay? So for this particular quiz, you guys are welcome to use your books and your notes, because it'll be a little bit more, describing concepts and ideas and that kind of thing. So there you guys are. Okay. All right, so I think that's all I kind of have to talk about or share with you guys initially. But anyway, before we launch back into it, then we'll start with prayer. But Lord, we just thank you yet again for another day and another chance and another opportunity, Lord. And you've given us the blessing of this day, Lord. And we pray that we can just be good stewards of the time that you've given us. And just, Lord, with the gifts and the talents that you've shared with each one of us in this room, Lord, we just pray that we can use that and be a good and faithful servant to you, Lord. Just help us to share your kingdom and help us to share the joy that's in our heart because we know you, Lord, with whoever's around us. Lord, give us your eyes to see those people that we need to talk to today and that we need to interact with and that we need to just lift their spirits, Lord, in whatever way that might be, Lord. Just give us your words on our lips and on our hearts when we run into them today. Let me just pray this in your name. Amen. All right. So cool. All right. So there's that. Hopefully we got the entropy part. Entropy. I keep confusing it for whatever reason. I don't know. All right. Yeah, no, it's just we talk about enthalpy a lot more, and so I just kind of get in that habit is what it is. All right, so here's another idea, which we'll come back to later. Like I said, the first couple of chapters of Gen Chem 2 are a little bit strange. We're kind of bringing in bits and pieces from different parts of other chapters. So we talked about how solubility of solids increases with increasing temperature, and like I said, I really can't think of an example to show or a counterexample, I guess I should say. I can't think of a solid that gets less soluble at higher temperature, but I'm sure something exists, but that's okay. Solubility of gases is the exact opposite. There's, as soon as you start to increase the temperature for a gas dissolved in a liquid, then the solubility starts to decrease, right? And this is why you guys keep your sodas in the fridge, right? Because as soon as you open them back up and you break the initial pressure on that sealed system, right, then if it's at room temperature, you're going to be releasing that CO2 at a much faster rate, right? So we keep it in the fridge, kind of keep everything, in solution, that kind of stuff there, right? Now, if you see there on the second line, I talk about something called Le Chatelier's principle. Le Chatelier's principle is one of these very important ideas that is present in all of chemistry, okay? We're going to introduce it here in Gen Chem 2, and when we talk about equilibrium, which is in 2 chapters? I know we do kinetics next, and then I forget where equilibrium comes in, but it's pretty close to the start of the semester here. We're going to talk about Le Chatelier's principle there quite a bit. For the moment, Le Chatelier's principle is a sea salt, okay? You guys, that's still something you guys had growing up back in my day, right? I don't know. You guys know what a seesaw is, right?
Yeah.
So you have it's one of these basic ideas of physics, right? You got you and your friend on opposite ends, and as you shift the weight, one side goes up and one side goes down, right? That's what it is, okay?
That's the Cleveland method. The pro method is you put a little kid on one end on the bottom, and then you get a really fat kid to climb up to the top of the playhouse tower and jump down, land on the other end, launch the little kid.
Sounds like something straight out of a cartoon, right? So.
It can be done.
Okay. All right. Anyway, so when we have a seesaw, right, we're just kind of, one side influences the other is what it is. And that's what Le Chatelier's principle is. So remember, one of these ideas that we talked about last time is of equilibrium. Remember when you guys see those arrows pointing in opposite directions there, one forward and one backwards? I'm saying, hey, look, whatever system we're discussing here is at equilibrium, okay? And so Le Chatelier's principle is just how we can influence which side of the equilibrium is favored. We can push it to one side or we can push it to the other. And we'll talk exactly about the who, what, when, where, and why when we get to the equilibrium part of that, okay? So don't worry about it when you read in the book at the moment, or if it's on my slides right here, right? We'll get to that stuff. And this will make a little bit more sense as we move a little bit further along, okay? All right. So anyway, so there's that. You got the idea. Gases, increasing temperature, decreasing solubility. Got it. All right. So the other end of this is actually something that's relevant, becoming more and more relevant each day. The idea of Henry's law here, and the solubility of gas is proportional to the partial pressure of the gas above the solution. Okay, what does that all mean, right? So we can measure the solubility based off of the pressures, right? That's all we're really kind of talking about here, right? So a relatively simple equation there, S equals K, which is the constant times the partial pressure of the gas. S is the solubility. We have some constant which scales this or proportions it, whatever you want to say. And then we have the pressure there, okay? Now, why is this important? Why do we care? What's this useful for? Well, one of the, let's say, the current focuses in research is about carbon capture, right? So knowing the solubility of CO2 in the carbon capture systems that we're trying to develop is extremely important, right? The other end of this is when we're talking about alternative energy, right? We're going to talk about hydrogen storage, right? We have to be able to absorb the hydrogen into whatever material that we have, right? Or we have to be able to store it in some way, those kind of things, right? So that's all this comes down to. In the scientific literature, this is how we measure the solubility of things, right? We're able to measure the partial pressure, and then we can back out the solubility based off of this relationship here, right? So not all science has these big scary equations that go along with it. Yeah?
How come helium's partial pressure is so low? Is it just because it's small?
Great question, right? It's a good observation. Why, right? Why would helium have a low solubility? Now, what does solubility come down to?
How easily something dissolves?
Yeah. I mean, that's kind of another way of just saying solubility,
Yeah.
right? What influences solubility? Yeah.
How strong are the intermolecular forces?
Aha, right? So that's what it comes down to, right? So remember, all we've been talking about for the last 2 chapters is basically the intermolecular forces and the balance that happens between breaking things apart and putting things together and rearranging molecules and all these kind of things that come from that, right? So the same idea here comes from solubility, right? If I want to dissolve a gas into a liquid, remember I've got to move the liquids apart, I got to put the gas in there, the liquid then, or the solvent then has to surround the gases, and that has to be better than the gas kind of hanging out on its own, right? So there has to be a gain or a loss of energy for this to happen, and that's the game that we're kind of playing with this, right? So the idea of solubility comes down to intermolecular forces also, is what it is. Now, then
Question.
well, hang on, I didn't answer your question yet, right? So to answer your question, why would helium and a lot of the noble gases have very low solubility then in most any solvent? Yeah.
Because it's a single atom instead of a molecule that has to be like separate.
Atoms still have intermolecular forces, right? You're on the right track, but what are you trying to say?
They don't have to be separated to be, I have no idea, Don.
What's up?
Well, it has its complete offset, so it probably doesn't want to share electrons.
Okay, so you're absolutely correct when you're talking about making a covalent bond to something else, right? So remember, when we're talking about bonding our noble gas to something else, that's our argument there, right? From how the electrons are arranged, right? But why? What intermolecular forces are present in helium?
Dispersion?
Hmm?
Dispersion?
Dispersion, that's it, right? How many electrons are present in helium? 2. So how big how polarizable are 2 electrons? The answer is not much, right? So you don't have a dipole, you can't do hydrogen bonding, you've got a very, very weak dispersion force, right? So what's gonna keep it in solution? Nothing, right? But then if you take a look at something like CO2, CO2 isn't even on there. Oh great, never mind, I can't do that. But anyway, so, just for argument's sake, I guess, you guys have heard of like nitro coffee, right? Where they try and dissolve nitrogen gas in a coffee, right? So there's a problem with this, right, that nitrogen isn't nearly as soluble in water, right, as something like CO2 is, right? You could make fizzy coffee if you wanted to, right? In fact, some companies sell that, okay? But nitrogen isn't nearly as soluble in water as CO2 is, and we could ask the same set of arguments there. Why wouldn't nitrogen be as soluble as CO2? It's a good question, isn't it? Thank you. 3 of you agree. And the rest of you guys are like, I need more coffee. Okay. Okay. Why? What's different between CO2 and N2 that will make CO2 more soluble in water? Yeah.
CO2 has dipole,
Okay. So what would that mean?
more intermolecular forces, greater solubility.
So it doesn't have a net dipole, does it? I'm not saying you're wrong, but just be careful what we're saying with the dipole. Yeah.
I think simply it has more electrons than nitrogen.
That's another argument to be made there, right? Remember the same argument that we just talked about with helium, right? Why does helium not have a lot of intermolecular forces, right? It's because we can make an argument based from dispersion, right? About how many electrons there are and how well those can start to polarize and make partial positives and partial negatives, right? So why would CO2 then be more soluble in water? Okay, so what's the name of the game? How do we predict solubility? What's our 1-sentence statement for looking at whether something's going to dissolve or not? 3 words.
Like dissolves life.
Like dissolves like. Got it? Right, so if I have similar properties, then it's more likely that I'm going to be soluble. What do we know about something like water? Got hydrogen bonding. Okay, well CO2 doesn't have that. Water is also very polar, right? Now, does CO2 have partial positive and negatives? Absolutely it does, right? Based off of electronegativity, right? Overall, it's not polar, right? It doesn't have a net dipole, but the individual components have partial positives and negatives. Got it? In fact, CO2 belongs to a class of gases which might be collectively, which are collectively termed acid gases. And this is important when you go read stuff about, carbon capture systems and things like that, right? And why would we call them acid gases? Great question. We'll talk about it in a later chapter. Okay. So, what's up?
Excuse me, I just have a quick, clarifying question.
Uh-huh.
How can you have a partial pressure if it doesn't have a net dipole?
How can you have pressure without a
Partial positive.
Mm.
Partial.
Great
partial
question.
charges.
How do we end up having any partial positives or negatives to begin with? What's the underlying principle?
Any what?
How do we end up having any partial positives or negatives? Ignore the idea of a net dipole.
Only thing I can think of is like the example with London, how by chance one of the electrons are more concentrated on one side.
So that's an argument from probabilities, right?
Yeah.
It'll at some point in time that'll exist on one end over the other, right?
Yeah.
But I'm talking about within a molecule itself. What do we need to look for when we're looking for partial positives and negatives within a molecule, an individual molecule? What's so special about fluorine? What do you guys know about fluorine? Okay, fluorine's very electronegative. What does that mean? So if I'm fluorine and I'm bound to something, okay, how do I feel?
Very negative.
Right, partially negative, right? And how does the thing I'm feeling, or attached to feel?
Partially positive.
Got it? So where do partial positive negatives come from? Electronegativity, okay? Right, so remember, how do we know whether something's polar or not? What do we need to know? We need to know the molecular geometry. We need to know the electronegativity. Got it?
Thank you.
Mm-hmm, of course. Very, very, very important idea there. Yeah, what's up?
So basically, fluorine hates everything, but everything loves fluorine.
No.
I'm making a joke because it feels negative.
No.
I'm sorry, my brain is like not functioning this morning.
It's all good. Okay, so here's just a little bit more. I gave you guys the same slide twice. Aha. How much does it cost you guys each time to print out a page?
Like 10 cents.
Sorry, I cost you guys 10 cents there. I promise. I'll make it up to you later. Okay, so here's just a classic example of just an example of how to calculate solubility, what this might look like. Right? So we have an equation for Henry's law there that's got 3 components to it. Right? So I have to give you information about 2 of those. Got it? So real quick, see what you guys can come up with there. Pay attention to units. Okay. Always important. Remember, when you're putting everything together, when you're writing things out, make sure you have your units as part of your equation. Right? Cancel things out, double check things, that kind of stuff. Remember, what do the brackets around CO2 there in the question, what does that mean?
The molarity.
Molarity, the concentration, right? Yeah. So a measure of concentration. Right? You guys all kind of see where we're getting to with this here soon. Take a peek at our ones. Don't worry, it's already the second week of class, and I have to wake up early.
So, Doc, are we looking for 2 separate molarities?
Nope. I mean, you can look for it if you want to.
Yeah, but the question, I mean, is structured for us to find 1 molarity at the time of being, like, bottled.
No, just when it's open. We're kind of getting there. So that's what we got. So we got a constant there that it gives us 3.4 times 10 to the negative 2 capital M over atmospheres, right? And then it tells us the pressure is 4.5, right? The partial pressure of CO2, oops, no, excuse me. Sorry, the pressure, when the partial pressure of CO2 in the atmosphere, and then when it's bottled, and we got all that kind of stuff, right? Oh, I see what you're asking, I'm sorry. I misunderstood your question, I thought you meant for the end of it. No, we got one there. Right?
Okay.
Yeah,
I
so the
thought
pressure, no, I'm just, I was just being slow, right? 4.5, right? So we put those two together. Substance space. Right? So what do we got here to begin with? Right, we're calculating solubility when, right, when it's bottled, right? So we just have our constant, and it gives us the pressure when it's bottled up there, right? What are the units that we have?
Molarity over atmosphere.
Atmospheres, and atmospheres will cancel out, so we're given units of molarity, which is a unit of concentration. Got it, right? Is that answering part of the question that we're looking for?
Yeah.
Yes, right? So there you go. And if I did my math right, then for this part, I got solubility equals 0.15 molar.
I'm using a calculator.
I have to use a calculator too. Good? So how would we solve the second part of this question then? So we said when it's bottled up, it's got that pressure, right?
Oh,
And then I open it up, and it gives us the pressure of CO2 in the atmosphere, right? So we assume that it opened up and it fizzes, right? So we set up a second equation of S equal Kp, right? Does our constant change?
no.
I'll give you a hint, it's called a
Constant.
right? The constant's not gonna change, right? What is gonna change though? The pressure, right? So we got a lower pressure, and we should end up with a lower solubility at that pressure, right? So K is still the same, 3.4 atmospheres, right? And then pressure in this case, 3.1 times 10 to the minus 4 atmospheres when it's opened up, right? Cool. And if I did my math right 2 times in a row, then I get that as my concentration at the end there. Good? It's not too bad, right? What is this telling us though?
That we can't do math early in the morning.
That's not quite the lesson that I wanted to give, but sure. Right? What is this telling us? Solubility is also related to what?
Pressure.
Pressure, got it? Right, that's all it is. Which, I think you guys already knew that, right? If I'm under high pressure, right, I basically force the CO2 back into the water, right? That's all it's basically saying, right? Got it? Yeah.
Does this apply mainly to gases?
Yeah. This is for solubility of gases. Yep.
Okay, so how does this work with how when you shake the bottle, the pressure essentially increases?
Ah, great question. Yeah, right, so why would that happen, right? That's a good quiz question,
Please, for the love of.
No, right, so what are you doing, what are you doing when you're shaking things up, right?
You're adding energy to the system.
Yeah, right, and so you're basically just knocking that stuff together and it comes out a solution is what it is, right? That's all it is.
Then why does the sugar at the bottom
Hmm?
So then why does the sugar at the bottom?
You're changing the volume, right? If you're in a sealed system, right? If we're assuming the bottle's not gonna change, we decrease the volume. And so then it takes less gas to get to the pressure that we need to keep it in solution, right? Does that make sense?
Kind of.
Kind of.
It's too early for this.
Good.
Can we just get a bunch of soda bottles and shake them up and drop Mentos in for good measure?
No,
Wow.
that's the way the world works. Okay, so, here's just kind of the, I like the spaghetti graph there of different solubilities for stuff. But this is just, again, just kind of a quick summary of the things we've already talked about here, right? Solubilities of solids versus the solubility of gases is controlled by, or is dependent on temperature also, right? But as we saw there previously, then, it's also, we have to take into account the pressures that are present also, right? All right, so let's concentrate a little bit here. All right, so we learned quite a bit about number 5 in the last semester, right? Where we talked about molarity, which is moles per liter, right? We got a couple things to learn about this semester. We're gonna talk a little about parts per million, and we could expand it to parts per billion, parts per trillion, whatever it is, right? We'll talk about that very quickly. We're gonna talk about mole fraction, although we did kind of discuss this stuff already a bit in the last semester when we talked about percent compositions and these kind of things, okay? And then the big thing that you guys are going to be needing, at least for this chapter, is molality, right? So when you guys are going through the lab this week, molality is essentially what you guys are going to be using in terms of a measure of concentration, okay? So what you'll notice for the mole fraction and the mass percent here, and these kind of things, notice that the bottom part of this is always the total mass of whatever you're looking for there. That's kind of one of these easy to miss parts. I always have to double check myself when I do this kind of math. It's the total mass of the solution. So it's the solvent plus whatever is dissolved in it, okay? So it's the total mass of the solution, not the mass of the solvent. You guys following along with that one here? Okay, that's different from what we're expecting, okay? At least what we maybe not expecting, what we're used to if we're kind of looking at molarity, that kind of thing, okay? So total mass of the solution. So don't forget to put that stuff in there, right? And I just like the most evil looking mole there. I think that's why I put that for you guys.
How is he evil looking?
I don't know, he looks suspicious.
Have you ever seen G-Force? Now that's an evil mole.
I don't know what that is.
It's a movie.
Movie?
The protagonists are, super spy trained guinea pigs, and the antagonist villain is a star-nosed mole who wants to take over the world using kitchen appliances.
How much money did it cost to make that movie?
Probably millions of dollars. It had a lot of special effects.
No, don't let me tell people how to live their life. But, you know, it's like if that money went to science instead, I think the world would be a better place. But just one man's humble opinion in the middle of Florida. What can I say? All right. So here's just a quick example of what you might see with this, and almost in a manner of I knew what was happening. I have the math up here for you guys, right? So here we don't have to actually calculate for yourself, but I think there are a couple examples coming up in just a minute about how to calculate some of these things, right? So mass fraction, the mass of the solute over the total mass, and then obviously if we just multiply that by 100%, then we get the weight percent out of it, right? So I think you guys know what a percent means at this point, right? But the book makes it very explicit, I guess, that weight percent is just, the percentage based off the mass fraction there. Got it? Right? There's nothing tricky about it, right? You have a fraction and then you multiply by 100 to get the percent. That's all it's really saying, okay? So what is the weight percent of sodium chloride in a solution of 4.6 grams of sodium chloride in 500 grams of water? So to get the weight percent, right, the weight percent, we need to get the mass fraction and multiply by 100, okay? That's all this question is asking, right? And like I said, don't forget this part down here at the bottom, right? It's not the mass of the solvent, it's the combined mass of the two together there, okay? So don't skip on that part when you guys are working through these problems in the book, okay? Other than that, math is easy, right? Good. Now, this is something, again, one of these concepts that's been coming up over and over and over recently. When we talk about, I don't know why I talk about so much about, well, I do know why, but apparently today is a lot of examples of carbon dioxide, these kind of things, right? So, they're always keep say, watch out for CO2, and they, you know, quote how many parts per million CO2 there are in the atmosphere, these kind of things, right? And so how do we actually measure a part per million, and how can we calculate it? Well, it's pretty simple, right? It's the mass of the solute divided by the mass of the solution times a million. Or if we're going to a billion, then it's times a billion, or per trillion, right? You guys get the idea? It's no different math than what you guys just saw in the previous slide there. It's just you multiply by million or billion or trillion or whatever it might be, okay? So question, the immediate question is, who cares, right? Why in the world would we care about this? Well, if you think about it, let's say I tell you something has a percent or that it exists in a 0.0001% of a solution. Wow, okay? What does that mean? Well, the reason why we talk and sometimes quote about parts per million, all these kind of things, is when we're dealing with really, really, really small concentrations of things. Instead of saying 0.0001%, we could say something like it is a 10 part per million, right? So it's really just kind of a mathematical trick if you want to think about it. It makes numbers a little bit easier to deal with, right? Which is kind of why we talk about scientific notation, all that stuff to begin with also, right? If you have really big numbers or really small numbers, then all we do is kind of scale it to something that's a little bit more manageable is what it is, right? It's really hard for us to kind of think of 0.0001% of something, but 10 is maybe a little bit easier for us to kind of grasp conceptually, right?
Are you saying we have stupid monkey brains?
No, I'm just saying it's a matter of you and I in our everyday life, we deal with, we don't deal with fractions of things all that often, right? We deal with whole numbers and, within a certain range, right? That's all it is, right? You guys got this, though? Right? Now, just as a little bit of approximation here, right? This is kind of similar to maybe what we expected to see with like some molarities there. A part per billion is about a microgram per liter. A part per million is about a milligram per liter. Now, you will notice I did not tell you it is exactly that, right? Right? Okay, right, so I'm again just kind of bringing this into, hey, remember we talked about molarity a lot last semester, right? So here's kind of something a little bit similar to that, just to give you guys an idea about why and how and just to conceptualize it a little bit here, okay? Definitely not something you guys have to memorize or anything like that, just, make it a little bit easier to comprehend, I guess. What's up?
Why is it approximately instead of exact?
Because it depends, right, how much, what 1 milligram, is, it takes up mass also, right? So, because you'll notice, right, it's mass over mass. Here I'm saying mass over volume, right? So we have different arguments to make there. Right?
Okay, thank you.
Good question. All right, now here's the moment where we need to pay attention again. Okay. Top part, you guys got, you understand it, 100%. We always remember everything from the previous semester. Good. Second part there, molality. Okay? So when you are dealing with the colligative properties, I'll introduce that idea in just a minute, right? But the freezing point depression and boiling point elevation, right? These are our colligative properties, right? We're going to be dealing with molality, right? So moles of solute, okay, over kilograms of solvent, right? So moles over kilograms. Now, one of the very, very, very important and fundamental things that came out of Gen Chem 1 is the idea of a mole, right? How much time did you spend calculating moles in Gen Chem 1?
So much.
All of it, pretty much, okay? So that idea is back here. Do you guys remember how to deal with moles? Thank you. Just lie to me, that's what I want to hear. No, I'm kidding, right? So, an honest question, if you guys are like, I don't really remember how to do that, I don't really remember where that comes in, okay? What do you think we need to do then? We go back and review it a little bit, right? So if you don't feel comfortable with calculating moles or, converting grams into moles and these kind of things, now's the time to take care of that, right? When's the worst time to take care of it?
During the exams.
The day after the exam, right? Or during the exam, right? Because guess what's going to happen then? Ouch. Okay? I'll go ahead and share a secret, okay? On the exam, there's going to be a question where you have to calculate molality, okay? I can tell from your stunned silence, okay? I'm made the whole room quiet and unresponsive with that question, or that statement, okay? But don't tell anyone else. Right? I don't think they can hear you too, so it's good, right? You guys are gonna nail it. They skipped class, right? F's for everything. All right, you guys with me on this? I'm just gonna, look, it's gonna be on there. You're gonna be asked to calculate molality. It's probably gonna relate to some boiling point elevation, freezing point depression, something like that, right? So if you don't remember about moles, you're gonna get it wrong. Okay, so don't do it. I'm telling you it's showing up, okay? All right. Oh, yeah, real quick. So I know I mentioned this earlier, but I talk fast and I say a lot of things. So why do we care about molality? Why in the world would we want to introduce another form of concentration? Well, it uses solvent mass, right, which is different, and it's temperature independent, okay? So that's the real idea there. When we're dealing with shifting temperatures, we need to pick a different unit of concentration, and that's why we have molality come up. Yeah, what's up?
So, I'm completely brain dead, but I
No,
genuinely don't.
you told us about your gerbil movie, but.
Guinea pigs.
Guinea pig, sorry, yes.
Why is molarity dependent upon temperature?
Ah, good question. I'll give you my second favorite cop-out answer for that. It's a great question. I like the question. Come see me in office hours for that, right? And we'll explain there.
Okay.
It's a good question. It really is a good question, right? So, now, you already know the answer to it. But because, like you said, maybe it's a slow warning, right? Then maybe it's kind of.
I think I might be having a slow week because yesterday Dr. Khan had to spend 15 minutes explaining how to do a basic multiplication to me.
Oh, he had to do his job as a professor. That sounds terrible. All right. Okay, so commercial 30% hydrogen peroxide has a density, and it's asking what is the molarity, right? Excuse me, yeah, molarity. Okay, so going back a little bit to molarity there. So to calculate molarity, not molality, calculate molarity, what do we need?
Molar.
Moles and volume, right? Liters, okay? I gave you a percentage and a density instead of any of those things, right?
Well, the density is kind of.
Right, but what's the use of density? Density helps us to shift between what units? Between mass and volume, right? 30% means what? Let's say I have 10 million liters of hydrogen peroxide, and it's 30%. What percentage of those 10 million liters is hydrogen peroxide?
3,000.
30%, right? Maybe I do need to explain basic multiplication. Right? You guys get what I'm saying? What if I had 0.00001, right, liters of hydrogen peroxide? What percentage of that would be hydrogen peroxide? 30%. You guys get what I'm saying? Does it matter what you start out with? No, right? 30% is 30% of whatever you're talking about. You guys following along what I'm telling you to do? What would make our life easier? What would make our math easier? What if we assume we have 100 grams of solution to begin with, right? You guys with me on this? If I have 100 grams of my solution, and 30% of that is hydrogen peroxide,
You have 30 grams of hydrogen peroxide.
see, you got it. It took a couple times. You guys with me on this? Does it have to be 100 grams? Could you have picked 1,000? Could you have picked 1,000,000? Right?
Yeah, but 100 is such a nice number.
Makes the math easy. So work on that. Assume you have 100 grams. And see what you guys come up with. Hmm. Mass divided by, right? Density is mass divided by volume. That's D times M. D equals M over. So be careful, right? I'm trying to calculate the molarity. So we need like mass need. Excuse me, moles and need. Yeah, right. So what is the right? What is the molarity of the constant of the solution, right? So we need moles of hydrogen peroxide. So molarity, we need moles and we need liters. Right?
Peroxide is O2.
So we have 30 grams of okay. So 30 grams of hydrogen peroxide we need. Okay. So grams into moles. What's that? So we start out by assuming 100 grams of what? The solution. And what do I give you information about? The density of the solution, right? So can we take 100 grams into we sit in the corner, so we're convert what to liters? The answer is yes. But of what, right? Where do we use that is what they're asking. Remember, what's the first assumption we made? We started out saying that we have 100 grams of our solution. Got it? You will need to do that. Be careful with the molar mass of no, that's not right. So, same question, right? We need to get moles and we need to get moles of what?
Stupid,
We'll
don't.
get to that. So moles of what? So how many grams sure, 30 grams in
Andy,
solution.
I'll send extra.
So those are the two values that you need. 30 grams hydrogen peroxide, 100 grams of solution. Got it? There you go, there you go.
Something.
So, let me, okay, I think everyone's kind of getting tripped up here, so let me see if I can help everyone. Okay, so let's think about this for just a second. I think we got off track here a little bit. We have to start out with an assumption, right? We have to take this and turn it into something meaningful for us, right? So remember, if I have 30%, it doesn't matter. I can pick any number that you guys want, okay? What is this telling us? 30% of a solution is hydrogen peroxide. Got it? You guys understand what I'm saying here? I'm saying that if I have 100 grams of solution, okay, I have 30 grams of what? Hydrogen peroxide. Got it? Now what do we need to do to answer the molarity? We need what? Moles of hydrogen peroxide. Okay? We have grams of hydrogen peroxide. Can you guys convert grams into moles? Yes. Yes. To To do molarity, what do we need? Liters of
Sorry.
solution, right? Liters of solution. Do I have a mass of a solution? Yes. How do I convert mass into volume? I need density. You guys with me on this? So remember, what is we have to write down what our starting assumption is. We assumed 100 grams of solution. Okay? This is what I mean by keep your units with you, right? 100 grams of solution means 30 grams of hydrogen peroxide. Good? Yeah.
The density is hydrogen peroxide.
The density of the solution, right?
Of the solution.
Of the 30% solution has that there, right? Because this would be a solution in water.
Yeah.
Because the density of water at 25 degrees, you would assume be like 1 or something like that, right? But this is a 30% solution has that density.
Okay,
Make sense?
I think so.
Okay. You guys with me now? Let's see what you guys come up with then. See if you can start to do the mathy part. What's that? Yep, looks good. Perfect.
Using, conversion factor, 1.11 grams of your hydrogen peroxide.
Right, so, again, I go back to the question of, if we're trying to calculate molarity,
It'd be 30 over 1.11.
liters of solution, right? So density is a way of,
Right, but I mean.
what's the
what number would
relating
be
mass and volume, right?
Be 30.
So look what we have in the
I
book,
chose
we have
100
mass of the
grams.
solution. But we need
30
what?
grams of hydrogen peroxide
Volume
in
of the solution.
100 grams.
So we have the mass of the solution, we have the density of the solution, so we need to just rearrange
What liters would you use that?
volume of the
Saying,
solution. Got it?
this is the hydrogen peroxide density.
I was looking over here.
So in that respect, you have to use your 30 instead of 100, because if you use the full solution, then your density will reflect not.
Oh, density is a property of whatever it is that you're looking at, right?
I'll say that one more time.
So
The
to measure this, all you do is you
100
go get a milliliter and you put on a balance and you just put the weight, right? And that's the density of, right? You can have what the density is based on that.
What number under the third would produce your density of 1.11? You can't
This is the density of
using
what?
100 grams.
Yeah, it's not that
Of the solution, right?
Yeah, that's what you guys done.
So you have 30 grams of hydrogen peroxide. How much solution do you have? 100 grams. So what's the volume of 100 grams?
You can like review all of it.
That's what you're trying to figure out, right? Right, because this is, remember, density is a way of relating mass and volume. I give you the, or we assume a mass, right, but that's the mass of our solution, right, but we need a volume, so what do you need to do? Just kind of rearrange the equation itself a little, right? Got it? Are we doing that here?
Again, I understand, like, kind of, the back part of my brain is following this, but the front part is actually.
So, this is density of solution. Right, be careful, density of the solution, right, so the overall, that 30% mix has a density with it. Good.
Did you guys finish?
Yeah.
Did you get,
Yeah, you can, well, here we have the two separate. So we have to figure out the moles. we have to
Wait,
figure
you
out
got
the volume.
32?
And then you bring it to the average.
0.11.
Right?
What did you get?
0.11.
So maybe
Did you get it, Donna?
9.79, the three of us got that.
It's a little bit more difficult.
I'm interested to see what I did wrong.
Harder as it goes on, right? Right?
Did you use 30 for your density?
It's 100.
30 out of 100, so point. Oh, for density?
Yes.
It gives you density.
I'm saying when you used it as a conversion factor, what did you use for your grams? Did you use 30 or 100?
I used 100.
Why do you use 100 instead of
That's what
30?
he said. I don't remember. That's what it was. Full solution.
Right, so your final answer should be moles of H2O out of liters.
Okay, I'm getting your thing. I got your answer. But. Well.
You know what? It's right.
Okay, that makes sense.
Because we don't, so we say 30%, whatever it is.
My brain is fried.
I got 3 1/3 now.
Liters of solution to begin with?
What was your
And we
mole?
have 30 liters of hydrogen peroxide.
Final?
But we don't have a density of hydrogen peroxide, right? Because we have to get that in mass.
It's 0.03 moles
That
per
make sense?
milliliter when you multiply that
Kind
density
of.
by,
You're hitting on something important.
by
I don't
the
understand.
molar mass.
Okay.
Well, if you multiply this density.
Oh, I see what you're saying.
By the molar
You
mass.
really need to.
All I did, all I did was find
Get
molar mass and then another
Exactly.
find liters and then divide into two.
Moles is
Well, I think about different substances, about 30 grams times the molar mass, denominator. Yeah,
Can you convert
yeah,
that?
times the like the denominator, and then you get
I want you to show me.
She just like combined.
You want it up in
Like,
the-
no, you're fine later.
So do that. So write that down and show me convert grams as what's okay?
Right by point out. So it's 34.
O2.
Wait, how many milliliters?
No, that's kiloliters.
No,
That's kilograms.
well,
We're
that's
on
a
the other way.
Yeah.
Yeah, okay.
No, yeah, so you're off by 1,000.
Yeah, yeah, that's what I
Yeah.
Wait, Dr. H.
Yep.
So for the
It's like a kilo.
Of solution to begin with, yes.
Yes, okay. Great.
All right. So we need two things. We need moles of hydrogen peroxide, and we need liters of solution, right? Oops, I put those in the, next to the wrong thing here. Let's try this the other way around, right? Okay. Okay. All right, so how do I, busy thinking about hamsters or whatever, all right. How do we convert grams of hydrogen peroxide into moles of hydrogen peroxide? What information do we need?
Molar mass.
The molar mass, right? So I saw it as I walked around, everyone had their periodic table out, and they were busily adding this up, and then they said, this takes time, and so they checked Google, right? Right? So you need your molar mass, right? Okay. How do we convert grams of something into liters of something? What information do we need? Density. Got it? Right? Or density. What do I mean by 1.1 here? What's the question saying? I have a 30% solution, and its density is 1.1. Got it? You guys catch that? This is important. I didn't say the density of hydrogen peroxide is 1.1. I'm not dealing with hydrogen peroxide. I'm dealing with a solution of hydrogen peroxide. What's the density of water for all our purposes? 1, right? So we know we're not dealing with water, otherwise I'd say the density is what? 1. Right, so I'm telling you it's 1.1. Got it? So what does that mean? It has to be a solution of something, right? Something dissolved in water. Does that make sense? You guys follow along with this one? This is an important thing to recognize. The density here is the density of the solution, not of water or of the hydrogen peroxide, right? The two parts together. Good? Does this clarify things a little bit then? What we need to do, right? Let's do this part down here then, so 30 grams of hydrogen peroxide. And let's see, what number did I use? What is it, about 34 point something grams?
It's like,
Oh, two.
oh, I
That's
just
good.
used 34.
Yeah, you'll probably be fine with that.
I just figured water is like about 18 plus 16, so.
So I got about 0.8821 something, right? Good. Any questions about this very key important conversion, which you guys will see over and over and over and over and over again, all of this semester? Good. Okay. The complete silence of complete understanding. Yes? Good. All right. So there's our moles. We got that part. That's good. The next part here. 100 grams of solution times 1.1 grams for every 1 milliliter, right? And then what do I need to do? Milliliters into liters. You have to remember how to do those conversions. No, but Google does at the moment, right? Right? So how many liters of solution do I have then? Was it 0.0909 or 9009, right? Good. What information do I need to calculate molarity? Moles per liter of solution. Do I have moles? Yep. Do I have liters of solution? Yep. So how do I get my final answer? This divided by that. Good? And I got an answer of about 9.8 or something like that, right?
Yeah.
9.8 molar. Cool. Who cares? What does that mean? Right? 9.8. 9.8? Whoa! I was expecting like 9.4, but 9.8, holy crap. Right? So let's put this into context. That's what I'm trying to say. Right? What does 9.8 molar solution mean? It is really darn concentrated. Right? Does that make sense?
Yeah.
30% of what we have is this hydrogen peroxide. Is 30% a pretty high concentration of something? Yeah, that's a third of what's present is hydrogen peroxide. Okay? That's really darn concentrated.
That's what I used to bleach my hair.
There you go, right? But the point is, whenever you guys come to an answer, see if you guys, does that answer make sense? Okay? 30% of something is a big concentration. So we should expect to see a pretty high molar concentration at the end of it also. Okay? Now I know it's like, okay, 9.8, yeah, sure, okay, right? But just start to take a step back at the end there. And this is the other important part I want to get across to you guys. The questions in Gen Chem 2. Do you guys see how there's a lot of assumptions that get made? This is a very short question, right? It takes what? Basically one line to write it out. But there's a lot of assumptions going on behind the scenes too for you guys to pay attention to. This is the tricky part, okay? I'm going to say this, and at the end, I'm going to make another statement you guys aren't going to believe me, right? So I'm using my professor powers here again. I will not trick you guys in this class. I don't need to. Do you know why?
Because it's tricky enough.
It's already tricky enough as it is, okay? I'm not going to go out of my way to trick you guys, I promise. But what I am expecting you guys to do is to stop, to think, to pay attention, okay? Take some time before you grab out your calculator and that stuff and say, what in the world is this question even asking me to do? What do I need to calculate? What formula do I need to use? What are my units? All these things that go along with it, okay? The best piece of advice that somebody told me that I didn't listen to is what I'm going to tell you guys now, okay? And I know what's going to happen. Some of you guys are going to go, he's talking to somebody else. Okay? He's talking to the person next to me. I saw him, okay? Keep your units with what you're working with, okay? That's it. It's going to make physics so much easier for you guys, okay? It's going to make chemistry so much easier for you guys. Dr. H, I don't need to do that. I'm brilliant. Okay? You don't understand how smart I am, Dr. H. I got an A in biology. Okay. I know you guys are smart. I know that. That's not why I'm telling you guys to do this. I'm not saying write units to prevent the dumb, okay? What I'm saying is write units to make sure that you guys show me how smart you are, because then you guys will get 100s, okay? I will come lavish you with praise, or Jolly Ranchers, whichever one you guys prefer, okay? Or maybe both. You guys get what I'm saying? Just do it. Get in that habit, start doing it now, start paying attention to the units, and start asking, what is this question want me to calculate, and what are the units that I need at the end of the problem? Good. All right, I will see you guys on Friday.